body immediately starts to fight. So that way you hopefully either don't have symptoms, don't get ill, or you have a very mild infection compared to what it would have been had you not like trained your body to deal with it. So certain cells in the immune system are programmed to respond. The primary response is the first exposure response. So you're exposed to a pathogen or a vaccine. Secondary response means that you have remembered it from the first time. You're going to be very specific. You're going to kind of go through that response when you encounter it again. So this is kind of your like general timeline for a primary response. So you get exposed to a pathogen, you get a vaccine. Over time, your body starts to develop antibodies. Your primary response kind of peaks over here, and then you get a secondary exposure after that response is dip. And you'll notice that this is a much faster and stronger curve compared to the first one. So, like, you get sick, it takes a really long time to get over it if you're like exposed to a pathogen. But then, if you are exposed to it again in the future, obviously your body is going to kind of come back stronger and stronger than it did the first time. So we have two types of cells that are really important, B cells and T cells. So B cells, B lymphocytes, are going to mature in the bone marrow, and they make your antibodies or your immunoglobulins. So you hear about the IgG, IgA, IgM, IgD, all that. So those are antibodies. They're extremely important in terms of fighting pathogens and toxins. That is referred to as humoral immunity. T cells or T lymphocytes mature in the thymus. They coordinate your innate and your adaptive immune response. So kind of bring the tumor 17 and 18 together. They basically say, hey, that's a bad cell. Let me target it because it's infected and let me destroy it. So this is called your cellular immunity, or a lot of textbooks refer to it as cell-mediated immunity. So we have to kind of review the antigens, the antibodies. We talked about that before. So antigens are your pathogen-specific molecules, right? So you can have things like your PAMPs, your pathogen-associated molecular patterns, and they differ, right? Because antigens are very specific. So when we talk about PAMPs, we're talking about like peptidoglycan gram-positive. Well, all gram-positive have that, right? So when we talk about pathogen-specific antigen, that means that we find this in staph, but we don't find it in strep. So we're going to kind of use these to stimulate production of antibodies, stimulate that cellular immunity. Sometimes they refer to them as immunogens. I typically see them referred to as antigens. So we can kind of have stuff for bacteria associated with flagella, capsule, cell walls, extracellular toxin, enzymes they secrete, so on and so forth. Then we talk about viruses. Viruses have their capsids, right? They're like protein layers. Some of them have spike structures, or they have envelopes, and that's kind of where we're getting that material from. All right. So there's no specific class of biomolecules for antigens. A lot of times they are proteins, but we also see carbohydrates, lipids, nucleic acids, and combinations of all of those together as well. Whenever we have antigens from different classes, depending on that class, they can kind of stimulate the response in different ways. So like protein versus the others, we're going to see a little bit of a difference there. All right, so however complex they are is important. So more complex molecules are more effective. So the more detailed it is, the more specific that response is pretty much the rule there. So structure and function always go together. Anytime you take anatomy, it's all about structure and function. If it's not shaped this way, it doesn't work that way, right? Alright, so your 3D structure of your antigen. So this gray blob is an antigen. It's going to contain stuff called epitopes, which are basically little regions that stick out on the surface of that antigen. So these are your little epitopes. Fun note, when I was making this PowerPoint, I was told my daughter, and I was like, "Can you gonna work?" And so she came back to my lab, and I was teaching her about this. And so she was sitting there like, "Antigen, epitope." And then I was like, antibodies, like your IgG, and this is where it is. And she was just like, yeah. And then she finally was like, and got down and walked away. It was like the most satisfying moment because she was like, I'm gonna watch Moana instead. And I was like, anyway, I bored her into submission. All right. So she'd be really smart for that maybe. Okay. So anyway, so little things that stick off the sides of the antigen. You can have several different types of antigens, and then again, that's going to make it more specific in terms of how it interacts with the antibodies as well. So if we kind of think about our antibodies, we're used to these little Y-shaped things, right? So whenever you kind of think about the potential, you're kind of depending it on your antigen size. Large structures have a lot of epitopes. Smaller molecules are not going to have that many. We also have like little free epitopes that are not actually part of the complex 3D structure. So those are called haptens. We hear about haptens a lot when we talk about allergic responses. So there are hapten-specific antibodies. A lot of times they attach to like a carrier molecule, like a protein, and then create what's called a conjugate antigen. So they're like attached. But those are small molecules that are free. But again, when we're kind of looking at this antibody antigen interaction, your antigen is here, your little shape sticking off the edge of your epitopes, and you'll notice that your antibodies interact in specific ways, right? The triangle, the green, the rectangle, whatever there, right? And you got that even Y shape. So shape our antibodies, and you can even see a yellow one with a circle down here. Those are your nice little Y shapes. Alright, so review of antibodies, proteins present in blood and tissue fluids that can participate in immune reactions. There are 4 protein chains that are held together in the shape of a Y. 2 large chains make up the heavy, 2 small chains make up the light chains. The arms are called the Fab region. Fragment of antigen binding is what that stands for. That is going to be the far end that's variable. So that's where they kind of differ for what they attach to in terms of the antigen. Bottom is called the FC region, fragment of crystallization is what that stands for. And that's where you're going to have complement factor binding and binding to phagocytic cells. So basically that's where they get kind of like flagged, like, hey, I'm bad, get rid of me. All right. So this is your picture of your beautiful Y-shaped antibody. Here's your like 3-dimensional structure that they look like. So if you ever go to biochem or anything like that, you're going to get more into this type of like understanding how the proteins form and all that. Okay, and they're always connected by these little disulfide bonds right here that we find on cysteine. All right. So your classes, this is kind of like the cool part, I think, like this in the vaccines, and talking about the responses. The rest of it kind of gets a little in depth. So, kind of hang on a minute here. So your classes of antibodies, when you hear about IgG, IgD, IgA, they're very similar. But they have unique heavy chains. So we're going to kind of see a difference in the presence of them in serum. We see differences in arrangement, where they're located in the body, their size, how they function. So IgG is your big boy. That is the most abundant one that we find in human blood. It can penetrate tissue spaces, so it can even cross the placenta. Again, we can't remember when we Googled what a placenta looks like. That's the organ that develops when you're pregnant that allows you to kind of like take your nutrients from your body and feed it to your baby. So IgG can actually cross that and provide immunity to a developing fetus. And IgG is going to be very versatile because of that ability to kind of move. IgM is a membrane-bound form. We're going to see antigen binding receptor like on our B cells essentially. That is the first antibody that we produce and secrete when we're talking about B cells. So it plays a large role in that primary and secondary immune response. And a lot of times IgMs serve as a diagnostic marker. So we're looking for that to identify an active or a recent infection, depending on the amounts of those levels. It's a very common abundant class found in mucus. So whenever we talk about mucus secretion, it can actually help track the pathogen to eliminate them from the body. Kind of like tracks them and like bring them over. We find IgA in breast milk, tears, and saliva. So whenever you're breastfeeding, one of the things that they always say is like a huge advantage. And again, breastfeeding is not easy, so if you can do it, cool, but don't feel guilty about that. But IgA can kind of pass through breast milk, so that's that antibody transfer to mom and baby. So obviously not found in formula, but is an advantage in your breastfeeding. All right, IgG, membrane bound, found on the surface of your B cells. Not secreted, very little is detected in the serum. IgE is the least abundant. It's very much associated with parasite events. And so we're going to see binding to basophils and mast cells. And a little bit of a difference here. We also see IgE can pop up with those allergic reactions for that. So here's kind of your different shapes. So I tried to like stay out of the like pentamer versus dimer kind of bit. But if we look at a pentamer, there's 5 of them and they make a pentagon, right? If we look at a dimer, there's 2. But a lot of them. So you can kind of see the numbers that you expect to find in your serum. Again, you see IgG like 80%, right? And then the rest are much, much smaller numbers. Panic-copy placenta. What are the functions are all kind of listed here in that table and nicely summarized for you. So a lot of this is kind of immunology topic, but just to kind of touch on them briefly so you understand how your body responds to infections, right? All right, so antigens and antibodies. Obviously, they interact. Their interaction is the whole basis for our immune system working the way it does. It's honestly like miraculous that we actually get sick so much because our immune system is very efficient. So when we talk about antibodies, we're neutralizing, we're opsonizing. Whenever you see opsonize, just think of it putting a red flag on that cell, like, hey, there's something wrong with me. Agglutination, so think about like when you did your blood typing, some of you did that, right? You used that clumping. Antibodies play a huge role in the ability to do that. There are agglutination assays that you can do for staphylococcus, streptococcus, mono, and then there's another one, Craig's. I'm forgetting it's crypto something. Anyway, but there are certain tests that they literally do in hospitals to identify specific types of strep or staph, right? So, like staph aureus is going to give a positive response to the agglutination reaction versus staph epi. And maybe if I know I have a staff kit, so maybe if I have time today, I can get some cultures prepped and we can look at one of those. It'll be the first time I've actually used the kit now. Maybe we can look at that and you can actually see how we do that kind of testing. But I have a friend that works at ECU Health. She says they regularly do that with mono and whatever that crypto one is. Like that is a very common agglutination assay. But it's based on these interactions. We also have complement activation and antibody-dependent cell-mediated cytotoxicity. Cytocell toxicity will kill, right? So killing cells that are infected. So we're going to kind of connect with all these parts, our innate immune system, and our adaptive immune system. So kind of taking that non-specific and moving into specific. All right, neutralization. Basically, I am binding to these epitopes on this pathogen or this toxin, and I'm preventing it from binding myself. So I kind of put it so that it can't actually attack. It's not going to do anything harmful. So I'm manipulating on that. Opsonization, I put a red flag on it. I say, hey, phagocyte, come over here and eat me. And that is your IgG. So this is kind of looking at neutralization. So you can kind of see if I kind of clog it up, I can't actually attach. And so that's not going to get onto my target cells. It's not going to or it's going to lessen severity. It's continuing. If we look at an opsonin, so opsonization again is basically like a huge red flag. It says, hey, I have a problem, get rid of me. Phagocytic cells like they come on over here and look at what they're doing. They're phagocytizing this little pathogen. They're going to be like, oh, no, Cookie Monster style. And then bye-bye bacteria. Clearly, I watched too much Sesame Street. Sorry. All right, but again, get a visual. They're not blue, unfortunately. Elimination. So here's your cross-linking of pathogens by the antibodies, creating these large aggregates. IgG can clump the pathogen cells together. That makes it easier for the kidneys and the spleen to filter them from the blood. So your kidneys filter your blood. A lot of people think kidneys just have to do with urine, but urine's getting rid of your bad stuff. Kidneys don't work, you are in a serious situation. That's why we have dialysis and stuff, right? So your kidneys play huge roles in filtering your blood. And this kind of assists in getting rid of those aggregates, right? They make them easier to filter. All right. So, when we talk about getting rid of our pathogens, we're going to kind of move into complement cascade and then cytotoxicity, right? So, Complement cascade is important for innate. We talked about it in chapter 17. It basically allows us to get an inflammatory response. So we're going to send phagocytes to the site of the infection. They're going to cookie monster the pathogens, right? And then we're going to kill gram-negative bacteria using our membrane attack complex, our MAC. We talked about that in chapter 17. So we're really focused on that classical pathway. Remember, we had like 3 pathways. The classical was the one that deals with these antibodies, the IgG and IgA. All right. Cytotoxicity, if we get rid of all the big words in front of it and just kind of focus on cytotoxicity, we're enhancing killing those guys, right? We're enhancing cookie monster. So we're going to have natural killer cells, the NK cells that primarily do this. Just going to build the macrophages come in and just stop. Additionally, once they kind of like nom that pathogen, right? They're gonna start to secrete these little so perforin. If I perforate my paper, like perforation, what does it do? It makes it easier to tear. And so what is that perforation like essentially when you look at your paper? What actually makes it easier to tear? It's half cut into. There's little holes. Perforin basically makes pores in the cell. It's the same idea, right? And then granzymes are going to come in and allow you to kind of just get rid of it. So very like effective enzymes in terms of getting rid of what's in there, right? So this is kind of your example here using a natural killer cell. We've kind of got these little cytotoxins that we're going to secrete. They make all the little holes, and then your granzymes are going to kind of take care of it here. All right, so major histocompatibility complex, MHC, is a term you're going to see a lot. I'm not going to write that big word out. The rest of the PowerPoint, MHC stands for that. So it's a collection of genes coding for specific molecules found on surfaces of any cells that have a nucleus in your body, right? So we're talking about host cells, right? So we have molecules on our healthy cells that mark them as self. They mark them as, hey, I'm normal. Let me pass through this little stop, and I'm going to move on with life. We also have a major role of kind of thinking about these versus things that aren't natural to us and how we mark them as non-self, right? So MHC1 molecules, we find these. They're present on normal self antigens and abnormal or non-self pathogens, so they're going to affect T cells involved in cellular immunity. If we have MHC2, we find these on macrophages, dendritic cells, and B cells, and they're going to present abnormal or non-self pathogen antigens to an initially activated. So they kind of say, hey, we need to start dealing with that. So they differ in their structure. I'm not going to dive in a lot into the differences in their structure, but you can kind of see it here. Again, I'm taking out all of this kind of lingo. You don't need class. I'm not going to quiz you or test you on it. But just so you kind of see the difference between the classes, you can kind of see that here. And so they all have what's called antigen binding cleft, where you see this little dip for the antigen to these lines. So we'll mention that little cleft area, but I'm not excited more. All right, we also have APCs, antigen presenting cells. So these are your macrophages, your dendritic cells, and your B cells. They literally take an antigen and then they like pop it out and they present it. Okay, they're like, hey, check me out. Am I normal? Am I normal? That's literally all they're doing, right? That's the most simple way to explain it. So antigen presenting, then they present this thing to you, and then you decide whether or not it's dangerous. Alright. Because they ingest and kill pathogens that penetrate our first line of defense, right? They recognize them through non-specific receptor interactions. We also have B cells playing a role in producing and secreting antibodies. Antibodies are not phagocytic. They're little live, right? They interact with foreign pathogens or their free antigens using some specificity, right? When they bind, the B cell internalizes that antigen. So basically they pull the antigen in, get over lymphocytosis, they process it, and then they present it. They're like, hey, look at me.